Just as a reminder, we're doing chapters 9, 10, 11 here right now. These are all the calculus chapters. Remember chapter 9, we're going to have just a quiz on, and then 9 will also be kind of a part of the chapter 10 quiz and test. So we're going to kind of can't do anything in chapter 10 without stuff from chapter 9 anyway, so.
What's the other chapter 10 about?
More derivatives.
Oh, yeah,
Alright, so where we had left off, we had been talking about this idea of an instantaneous rate of change. How that this was really the same thing as if I look at the curve and I try to draw a line that's tangent to the curve at that point, the slope of that line should be the same as the instantaneous rate of change for that. And we gave that name, we call that the derivative of f at x equals a. So we wrote out some notations that we'll use for a derivative. So we can use like the d over dx notation that means like we're taking the derivative of this thing. And then I gave for you guys a few shortcuts on that you'll use to actually find the derivatives of stuff. So the derivative operation distributes across addition and subtraction, that you can pull a constant multiple out to the front, that the derivative of a constant is 0, and that the power rule for derivatives is the derivative of a power function, x to the n, is going to be n times x to the n minus 1. And for the most part, that with a little bit of algebra is going to be all we need to evaluate derivatives, at least as far as the IB is interested in being able to evaluate derivatives in this course. Shall we do a few more examples of that process of taking the derivative? We did a bunch of examples last time. This is going to be a core skill that you're going to be expected to be able to do. You should be able to do this quickly. You should be able to do this almost in your head. And if we don't feel like we're quite here yet, let's take a minute and do some more example before we move forward, because without this skill, there's no sense in like rushing our way into applying a derivative if we can't use it or can't, evaluate one properly. Everybody's okay?
All right.
So let's say we want to find the derivative of this function. So we could write like y prime equals, and what we're going to be doing is doing the derivative operation of that function called y. So I notice in that function called y, I see addition and subtraction going on. I know I can distribute this derivative operation across the addition and subtraction. To change this from one rather complicated derivative into 3 less complicated derivatives. Are you okay with what I did there? Now, additionally, I see that I have inside the first derivative and the second derivative that I've written up there, I have multiplication going on. Do you see where the multiplication is? It's happening between the 7 and the x cubed, and then the 4 and the x. So you see that? Now, I don't have a rule to deal with the product, like how to do the derivative of a product. There is one. You're not going to learn it. The IB doesn't expect you to use it. I'm not going to teach it to you. Instead, though, what I can do is, because those multiplications are constants, I can use my rules of derivatives and pull the constant out front. So I can do that. Is everybody all right there? Yeah. Now I notice that everything that's remaining that I have to take the derivative of is either a power function or a constant, right? Those are the 2 things that I have a rule to take the derivative for. So x cubed is in the form x to the n, right? My derivative rule says that the derivative of that should be n times x to the n minus 1. So the exponent becomes the coefficient, and then I subtract 1 from the exponent. And that works for all values of n except for n equals negative 1. Everybody's okay? So what will the derivative of x cubed be then? Right? The exponent becomes the coefficient, and we subtract 1 from the exponent. Okay? What am I going to do with x? Is that a power function? Can I write it as x to the n? What is n? 1. Okay, so what's the derivative going to be?
1x to 0.
And I'm going to write it as, with the subtractions there for now, so everybody's on the same page. And what's the derivative of a constant? 0. Okay, so think about it like if you graphed y equals 7, what does that look like? What's the graph of y equals 7 look like? Straight horizontal line, right? What's the slope at any point on that horizontal line? 0. What should be the derivative then? 0, because derivative is just talking about instantaneous rate of change or slope, and if the slope is the same everywhere, then the instantaneous rate of change is the same as the average rate of change, it's just 0. Okay? So this simplifies down to just be 21x squared plus 4. Everybody happy with that?
I'm just wondering, why wouldn't it be minus 4?
Oh, thank you. I made a mistake. Okay? So that's like the simplest kind of situation you can run into. Nothing needs to, there's no algebra that needs to happen beforehand. Everything is like loaded up and ready to go in a form that you can handle. Let's look at an example where that's not the case. Okay? So here's a new function that we're looking to take the derivative of. Notice here that right away, I noticed two things that weren't taking place in the previous problem. I have multiplication and division that involves the variable, right? You guys see that? So, before I can even think about applying my derivative rules, I have to clear that multiplication division hurdles. Is okay with that? To do that, I need to use algebra. So, the only thing I can take the derivative of are power functions and constants. I need to get this into the form where I have just power function and constants. So, I remember from my Algebra 2 class that every radical I can rewrite as a fractional exponent. So the square root of x can be x to 1/2. The cube root of x can be x to 1/3. And then what am I going to do with 7 over 2x squared? What don't I like about that? The x in the denominator, right? That there's a division going on. Now there's an exponent property here that can help us. So how am I going to rewrite 7 over 2x squared?
7x negative 2 over 2.
Great. I'm going to write it this way, though, where the 7 over 2 is just like a coefficient, because I know where I'm going with this, and eventually that coefficient is going to be pulled out front. So I'm going to make it like coefficient looking. But what you said was perfectly reasonable, totally correct, no problem with it. Everybody so far so good. Now how do I multiply x to 1/2 times x to 1/3?
Add the exponents.
I add the exponents. Another exponent property, right? Remember when your algebra teacher or your algebra 2 teacher told you that you needed to memorize these exponent properties, that like they weren't going away? They're not going to. Is everybody okay that 1/2 plus 1/3 is 5/6? What I do to add those? Made a common denominator, you know, like everybody's okay. I don't need to show that work, I'm hoping. Nobody's going to try to tell me that it's like 2/5 or something. Please, for the sake of the love of God. All right. And then I have this, still this fraction though, x to 5/6 over x. What am I going to do with that?
Subtract and get x to the negative 1/6.
Yeah. Right, we have that property of exponents. Okay. Now look at what we've done. Have we done any calculus yet? No. Everything that we've done so far is algebra. How do I know I'm ready to start the calculus? No more multiplication, division. Every variable is a power function or a constant. I'm ready to go. Is everybody good? Okay. So now I'm going to go ahead and take my derivative. Let's try to do this in one step instead of writing out every little nitty-gritty detail, because this is the second time we're doing this, and we'd like to kind of condense this down to be like a no work shown problem, at least at this stage. So because there's subtraction here, I can take the derivative term by term. So I'm just going to start by taking the derivative of x to the negative 1/6. What do I get?
Negative 1/6 x to the negative 7/6.
You guys see what Marin did here. Eventually, somebody other than Marin needs to answer these questions that I'm asking. Good job, Marin. So everybody's okay? So the exponent became the coefficient, and I subtracted 1 from the exponent, right? Okay. I'll write my minus sign, and then I'm going to do the same thing. What's the derivative of 7/2 x to the negative 2? Well, let's do this. Negative 2
1.
nope.
Negative 2 minus 1.
Negative 2 minus 1 is
Negative 3.
negative 3. Okay. And then we'll simplify that down. What do you guys think? Is this okay? All right, let's take a step forward then. If this feels like it's going okay. Again, we'll continue to practice on this skill because it's a must-have. We must be able to find the derivative of a function effectively, quickly, accurately, and ideally with very minimal work shown. Once you feel good about this, these are mostly things you should be able to do in your head. As we're approaching that level here on this one, right? Do you need to be able to do it in your head? No, but no one's ever going to ask you to do it in your head. You could write out more steps if you need to, but it should be something that's like, this is an easy enough process for me that I do feel comfortable doing this mostly in my head. Okay. So, who of us in here is in physics or now or past? Only a couple, huh? All right. Well, everyone else, you're going to get a fun little taste of physics here because the IB loves nothing more than to think you're in one class and all of a sudden you end up in a different class. Right? How often has this happened? Like, I thought it was English class and all of a sudden I'm in history or something, right? This is like par for the IB course. So, some important quantities and their derivatives. So in physics, the first thing you guys probably study is talking about kinematics, the study of how things move. Now it's a simplified version because they ignore a bunch of stuff, at least initially. So there are three primary quantities, and they're related because they are the instantaneous rate of change, or the derivative of the previous one. So if I take position, and I look at the instantaneous rate of change in position, we call that velocity. That's the rate at which position is changing. Everybody's okay with that? If I look at the rate at which velocity is changing, the instantaneous rate of change of velocity is acceleration. How is my rate of change changing? And the instantaneous rate of change of acceleration, that's named after Anthony. What is it? It's jerk. I got you good. So that's the rate at which the rate of change is changing. So it's like a third derivative, right? So you can say that like the first derivative of position is velocity. The second derivative of position is the derivative of velocity, which is acceleration. Or like the third derivative of position is the second derivative of velocity, is the first derivative of acceleration, which is jerk. Of course. Everybody okay with the relationship between these? Now, I wrote these all as DDTs. Why is this DDT instead of DDX?
Yes. Because time is X.
Because my variable in kinematics, the independent variable is going to be time. Yeah, we abbreviate time with the variable t. So my derivative operation just needs to match the independent variable in the question. So since position is a function s of t, the derivative operation should be ddt, where the variables match. Everybody okay there? Little thing, but again, like, you guys have never done this before, so one of those that probably we need to be clear about. Oh boy, what just happened?
Whoa.
Undo. Whatever it just did there, I didn't like that. All right. A ball is thrown upward from the roof of a building. The vertical height of the ball from the ground in meters after t seconds is given by the function h of t equals negative 4.9 t squared plus 18t plus 50. The derivative function is given as h prime of t equals negative 9.8 t plus 18. Let's just verify that, right? We know how to do that. Let's check that real quick. The problem isn't asking us to do that, but like it's a good opportunity to just practice. Okay, so I'm going to distribute my derivative and pull the constants out front. I'm going to do that all in one step. Does anybody object to me doing it that way? Everybody feel good on that first step? All I did there was distribute the derivative operation through and pull the constants out front. Okay. What's the derivative of t squared? Other than Marin and Emerson, who can tell me this? Derivative of t squared. Blake.
1t, 1 minus 1.
Close.
1t, 2 minus 1.
Close.
Or no, 2t.
2t to the 2 minus 1, so just 2t. Okay? What's the derivative of t? What's that?
1t.
Not 1t.
Oh, is it?
1.
This is 0?
1, yes. It's 1. It's 1 times t to the 0. Anything other than 0 to the 0 power is 1. That's why you thought it was. And then the derivative of 50 is 0. And this is exactly the negative 9.8 t plus 18 that they quoted us earlier, right? Everybody's okay? Again, problem didn't ask us to do that. We did it because we knew how to do it. It was good practice. Let's go ahead and do it. All right. The first part of this problem says find the initial velocity of the ball. So the key word there telling us what to do is initial. Right? If I want to find the initial velocity, if I want to find the velocity, it means I need a time to plug into my velocity formula, which is the first derivative of position. What time does initial mean? T equals 0, right? Yes, sure.
18
Meters per second? Yeah.
Yeah. So you just plug in 0.
Yeah. So my velocity function, and it should spit out velocities for me, right?
Can I take my water, please?
Sure.
Yeah.
Everybody's okay? Part B says, find the time at which the velocity of the ball is 0 and interpret the meaning of this. So it wants us to do this, right? Find when V of t is 0. My equation for V of t is so I just subtract 18 and then divide by negative 9.8.
I'll let you come to the office for a minute.
Yeah, of course. They want you might want to think about working on your dress code situation.
Yeah, I'll
Go down
change.
there and compound your problems. You're welcome.
We're back.
Is everybody okay with what I did here? And obviously that could be a decimal and round to 3 sig figs or whatever. I don't have a calculator sitting right here, so I'm just not going to bother with it. Does anybody object to me just leaving it as this stupid fraction? Is a rounded answer to 3 sig figs okay? Definitely would be. More appropriate in this situation than the fraction might work for. So far so good? Part C then says, find the velocity of the ball at the moment it hits the ground. So again, if I'm looking for a velocity, I need to have a time. Does it tell me the time in the problem? Not specifically, but it tells me how to find the time, right? What time, what happens at the time I'm interested in? What is happening to the ball at the time I'm interested in plugging in? It hits the ground. What does hits the ground mean? Is that talking about a velocity, a position, or an acceleration? A position, right? What position is the ball hitting the ground? What does that mean?
It's at 0 height.
Perfect, yes. So I'm going to solve for S of t equal to 0, and then I'm going to take that t and plug it into my velocity to find the velocity. Everybody good with that plan? Okay. So I guess I should say h, right? They said that since this is a one-dimensional motion, just up and down, they're calling it height, h of t, whatever. So this is the equation we're going to solve. What type of an equation is this? No. We're in Algebra 2 still right now.
Quadratic.
Quadratic, great. What are the different methods I can use to solve a quadratic?
Factor quadratic formula.
Factor quadratic formula, or there's still another good one. The one I would use in this situation on an IB exam. Graphing. I would graph and just find the zero, because I'm not really interested in doing the algebra here. If this is the IB exam, I have my graphing calculator the entire time, right? I would do that. Now, could you solve this by quadratic formula? Certainly. Guaranteed it's going to work. Is factoring guaranteed to work? No, and in fact, I would want no part of this with the decimal out there. I'm not really interested in that. And then the fact that the leading coefficient isn't 1 either. No thank you. Pass on this one. Even if I was dead set on using like factoring or the quadratic formula, I would not want to factor this. And in all likelihood, it's probably a decimal the factors are probably non-rational numbers, and it's not going to be factorable nicely anyway. So for me solving, I've typed in my equation to the y equals. I hit graph on a standard axis. I see I have two solutions. Which one is the one that I'm going to be interested in?
Positive one.
The positive one, the one on the right. Why is the negative one not of interest to us?
Time can be negative.
Time can never be negative, right? I'm solving for a time. The negative answer is meaningless to me, right? So I'm only interested in that answer on the right, so I'll do second trace. I'll pick the 0 command, left bound, right bound, guess. So 5.52 is answer rounded to 3 sig figs. But that's not what the question is asking me for, right? That's the time in which we hit the ground. The question asks us for the velocity of the ball when it hits the ground. So what do I still need to do? Plug that t into my velocity equation. So negative 36.1, we'll say. Meters per second. Now, does it make sense that the value is negative? Let's think about the situation, right? We got some person on top of a building. They throw the ball up, and it hits the ground. Right? So it makes sense that that velocity is negative.
Right.
Those of us that haven't had physics before, velocity is different from speed. How?
Isn't that like how a direction?
Velocity is a vector, so it has a direction to it. Yes.
Bouncing back.
So the negative velocity means the ball is moving in which direction, up or down? Negative would be down, right? Like you're traveling down on the y-axis, right? Which is what's happening when the ball hits the ground. It's moving down which should make sense, right? The ball's going to have a positive velocity up until this time, which was the first time we solved for when the velocity was 0. At the very top of the arc, the ball stops moving up or down. It's like hanging in the air for just 1 second, and then starts moving down. And its velocity becomes more and more negative the longer it's falling, right? Because it's picking up speed until physicists in the room, what happens? It reaches like a terminal velocity at some point where the friction of air offsets the acceleration due to gravity, and the ball would stop increasing in speed. Do you need to know that for this class? No. Is that just me enriching and connecting this to something you've done in physics? For those of you that are in physics, or have been in physics, yes, that's all I'm doing. Now, this idea of being able to move back and forth between a function and its derivative in order to solve a problem. This is not limited to just a physics situation. This happens all the time in many different disciplines. Econ people in here? Who's had econ or been in econ or currently in econ? Great. You guys talk about, what's it called? The marginal, what is it called? It's marginal something. Econ people. It's like the cost to make an individual product, like 1 unit.
Marginal cost.
Marginal cost, right? The marginal cost is a derivative of the cost function. It's looking at how much it costs to build 1 unit at different production levels. Typically, you see that the more you build, the cheaper it is to build the thing. Right? That's usually how business works. Eventually, up until a point, though, what happens eventually? You exceed your means of production, have to build like a new factory or hire more people or something, and then like you have another spike in costs, and you have to increase production until it gets cheaper than it was before you had to build a new factory. Does that sound familiar, econ people? Yeah, right? Like this world of the derivative, this world of calculus happens all the time in all these different disciplines that you weren't even expecting. Who's in biology? Yeah, right? You guys talk about like predator-prey model. Okay? And you talk about like the population growth rates involved with changing your predator-prey populations. Guess what that change is? It's a derivative. So like if you're modeling, like how that predator-prey systems behave as one population is increasing or decreasing, you're essentially doing calculus there. And to be honest with you, it's ostensibly the same model if you look instead of like at the macro scale, if you look in the micro scale, if you're looking at immunology, like if you're looking at epidemiology, how like a virus interacts with a population. It's kind of the same model. A lot of the same techniques are going on as the predator-prey model, where the predator is now just like the immune system, and the prey is like the virus inside of the body. So like this kind of thing has like huge sweeping applications all over the place in science and economics and maybe places you weren't even really expecting, or places that you've already interacted with and you didn't really realize what was going on there. But that's what's happening here. Now, some of those systems can be really complicated, and the techniques are way beyond the scope of the things you need to know for this class, where you're talking about like building systems of partial differentiable equations, which is just like needs a whole different scope of mathematics to deal with. That's probably what you're dealing with when you're doing epidemiology, because there's a lot of factors involved there. But at the most basic level, we can understand, some of these more basic situations through analogy of kind of what we're doing and what the relationship's going on here, and build a good foundation for if that is something you're going to specialize in at some point in your life. We've laid a foundation that you can understand, because it's like, oh, this is kind of like a marginal cost and cost function situation here. I remember doing this. Or this is kind of like, position, velocity, acceleration. I remember doing that. Where it provides like a good foundation for, understanding something that may be of more interest later on that's kind of the same relationship. Everybody okay? So what we're going to be building here towards is looking at, now we have this idea of what a derivative is. We've talked about in theory how we're calculating it, and then in practice how we calculate it. What we want to do is be able to talk about how can I use that derivative function to learn about the behavior of the graph of f. So the derivative, because it's a slope function, it's telling us about the slopes of f, can tell us where f is increasing or decreasing. Because what kind of slope does an increasing function have? Positive. What kind of slope does a decreasing function have? Negative. So if I can solve my derivative and find out where it's positive and negative, that can tell me where my function, my f, is increasing and decreasing. And what does increasing and decreasing allow us to tell? What does that help us find on f? So I go to increase, and then I change to decrease. What just happened?
When you have your highest value or your min or max.
Yes, it's going to help us find our maxima and minima. Exactly right. Changing from increasing to decreasing means we're going to have a maximum, and then from decreasing to increasing, that would mean we'd have a minimum. So the derivative is going to allow us to find the values of the maximum and minimum for these functions. And we can now do this, depending on the situation, algebraically purely, right? How were we doing this before? What do we have to use to find the minimum or maximum? Yeah, we had to graph it on our calculator and use the min-max commands, right? We could not find those values algebraically on our own. This is now laying the foundation for a method to do that without a calculator. Now, on the IB exam, are you ever going to be without the calculator? No. You always have the calculator. Now, are they going to cook up questions in which the calculator is not going to allow you to shortcut your way through this? Yes. So you still need to be able to find these values algebraically. Additionally, so if I look at the rate at which the slope is changing, that can tell me about the concavity. So the second derivative of f can tell me whether my function is concave up. So that's like a cup where it would hold water in it. Or concave down, that's like a hill where the water would run off if you poured it on it. So concave up would be that the rate of the rate is increasing, so the second derivative should be positive. and concave down would be the second derivative is negative. And then we can use that second derivative then to find the places where we change concavity, where the function changes from concave up to concave down. We call those inflection points. That should happen again where the graph, or where the second derivative is equal to 0, or undefined, I guess. I have to review how much we want to deal with non-continuity here. I don't think very much, though. I have to double check that. Is everybody okay with this ideas? So eventually what we're going to want to be able to do is we're going to want to use our first and second derivatives to analyze our function, be able to tell where the function is increasing and decreasing, where it has maximums and minimums, where it's concave up and concave down, and where it switches concavity from, or has an inflection point. So we're going to do all that kind of analysis coming up. Now, this is really important, and not just for this class, but in life, because the places where, or one very important application in almost every branch of, science or industry is something called optimization. When I say optimization, what are we talking about? Talking about finding the best way to do something, like best, right? So that could be the cheapest way to do something, which would be super interesting to most people in business, right? Like, what's the cheapest way to make this product? That's a ton of interest to us. Or it could be a maximization, right? Where it's like, oh, find me the product that does this the best, right? The vacuum that sucks the hardest. Or, like the paint that spreads the most, that covers the most surface area for 1 gallon of paint or whatever. So that process of finding the optimal way of doing something, depending on the circumstance, whether it's a maximum or minima, is of huge interest throughout industry, right? The way you would do that, or one way you can do that, depending on the situation, is using the derivative to analyze the model for your function to find where those maxima or minima lie. Okay? Now, there's one little hitch on that. So, what if your function is on a closed interval instead of an open interval? Right? What if it starts, does some stuff, and then it ends, and it's a hard endpoint? Well, those endpoints, those hard endpoints, those could also be a maximum or minimum as well, right? Now, they can't be a local maximum or minimum, but they could be the absolute or the global maximum or minimum. So depending on the situation, whether your domain for your function is open or closed, requires additional check to see if, oh, look at this, the actual absolute maximum is not one of the local maxes, it's the endpoint of the function. So we would be checking that manually, yes. In fact, we would check all of them and just see which one is the biggest to see if the endpoint was actually a maximum or not, just to see if it's bigger than all the other extrema. What do you guys think? So it's like a little bit of a preview of what we're going to be getting to. I don't want to get into that today because I have not enough time to really get into that too far. That feels like more than I want to bite off. at this point, so I'm gonna stop here. Next class will probably be finishing my goal is to finish chapter 9, so that I can give you the chapter 9 quiz as your virtual day assignment for Friday. Sound fair to you guys? It feels like a good thing to just here, work on this. Should be easy to take care of. Sound good to you guys? Okay.